Legend has it, a bored teenager sat in a cathedral in Pisa, watching a lamp swing overhead. And using his own pulse as a stopwatch, he noticed something strange. Big swings, small swings, they all seem to take the same time. That's a weird thing to notice, right? You'd think a wider swing would take longer. So here's the question we're really after. How does the angle change over time, and what exactly sets the rhythm of the swing? To answer that, we strip the problem down to its bones. A single point of mass, which we'll call m, hanging on a string of length L. The string has no weight, it doesn't stretch, and we throw away air resistance entirely. Just a mass, a string, and gravity. Now, the mass rides along a circle. So the distance it travels from the bottom, the arc length we'll call s, is just the radius L times the angle theta. That single line is the bridge between geometry and motion. Differentiate that once, and you get the speed along the arc. Differentiate again, and you get the acceleration. So the acceleration along the path is simply L times theta double prime. Here's where it gets good. Gravity pulls straight down, a force of m times g. But the mass can't go straight down. The string won't let it. So we split that pull into two pieces. One along the string and one along the swing. The piece along the string, that's mg cosine theta. But it does absolutely nothing to the motion. The string is rigid, so its tension cancels that part out perfectly. It's a tug of war that ends in a tie. So the only piece that matters is the one along the swing. From the little triangle, that's mg sine theta. And because it always points back toward the bottom, fighting the swing, it carries a minus sign. Force equals minus mg sine theta. Now bring in Newton. Force equals mass times acceleration. On one side, minus mg sine theta. On the other, m times L times theta double prime. And watch what happens, the mass, m, sits on both sides. So it just cancels. And out drops the equation of the pendulum. Theta double prime equals minus g over L times sine theta. Notice what's already gone. The mass is nowhere in sight. A heavy bob and a light bob swing exactly the same way. There's just one problem. That sign makes the equation nonlinear. And a nonlinear equation like this one has no nice, clean solution in terms of the functions, you know. So we do what physicists love to do. We cheat carefully. For small angles, sine theta is almost exactly theta itself. It comes straight out of the Taylor series. Sine theta is theta minus theta cubed over 6. And for tiny angles, that cube term is just noise. So we drop it. Sine theta becomes theta, and the equation turns linear. And this equation we know by heart. It's simple harmonic motion. Since the pendulum starts at rest, pulled to some angle theta naught, the answer is a clean cosine. Theta of t equals theta naught times cosine of the square root of g over L times t. It just rocks back and forth. Forever. And finally, the rhythm Galileo spotted. One full swing, the period, is 2 pi times the square root of L over g. Look at what's missing. No mass. No amplitude. The period depends only on the length of the string and gravity. That teenager in the cathedral was right. And that's exactly why the pendulum became the heartbeat of the first accurate clocks.